Hello and welcome to the Industrial Master Electrician. My name is Bill and I have 45 years experience in the electrical industry, including being a master electrician since 1992. In this video series, we will be discussing low voltage induction motors. This is part one, application and nameplate. This presentation is part one of a series on low voltage induction motors. These motors are the most commonly used electric motors in industry. We will not be discussing medium voltage, high voltage, or DC motors in this presentation as they will be presented in other future videos. We will be discussing three-phase AC motors rated under 1000 volts. We will first describe various applications for which these motors are typically used in industrial applications. This video is intended as more of an application rather than any kind of test prep, although it may assist in that regard. Again, this is for practical hands-on application in the field. The basic purpose of a motor is to convert electrical energy to mechanical energy in order to perform work. In this capacity, you will find motors used in a variety of applications, including pumps, compressors, conveyor belts, chippers, crushers, and hoists, including many other applications. This is just a short typical list and is not exhaustive by any means. We will take a look at a typical motor nameplate and break it down into the various information so that we can obtain from it the information to help us apply it to properly to our specific application. So in the first line here in the first box, we see above that is the catalog number. This is the manufacturer's catalog number used for the specific type of motor. Second number is the customer part number. Some customers will have a line of motors just for them, and they will have their own unique part number for the motor. Some manufacturers say may be manufacturing 14,000 components a year of some type of equipment, and they always use the same motor. Well, they can have their own part number, which is useful for supply and ordering uh, motors. The third box is the enclosure type. This is very important to know for the environmental conditions of the installation side of the motor. In this instance, it is a TFC, which stands for Totally Enclosed Fan Cooled. NEMA, the National Electrical Manufacturers Association, has designated frame types for various applications. Here's a short list of some of the types you may see in the field. Totally enclosed fan cooled. No ventilation openings, enclosed to prevent the free exchange of air, although they're not airtight, with an external fan as an integral part of the motor. The fan provides cooling by blowing air on the outside of the motor. This is the most commonly used. Weather protected, WP1, WP2. WP1 is an enhanced version of ODP, which is the open drip proof. The addition of screens to an ODP motor prevents the ingress of large particles from entering the motor. WP2 has, in addition to WP1, its ventilation passages arranged so that high velocity air and air particulates cannot be discharged without entering the ventilating passages. The flow path is designed for at least three abrupt changes in direction, none of which are to be less than 90 degrees. Finally, in this example, we have XP, which is explosion proof. Explosion proof motors are intended for use in hazardous locations in the presence of explosive liquids, gases, dust, etc. Locations are classified according to the nature of the hazard. Next, we have in the first box, line 2, the specification number for the motor. Most motors have a specification to which they are built, and this will contain that number. This number can be used to identify the motor for replacement. So you can call up, in this particular case, you can call up Baldor and say, hey, here's the spec number for this motor. I need a replacement, and hopefully they can provide you with a direct replacement. The second box is a CC, or certified compliance number. This is unique to the manufacturer and indicates that the motor is in compliance with the NEMA premium efficiency specification. The third box is the frame number of the motor. This number indicates all the dimensions for the motor and can be looked up in a table. The last box is a serial number of the motor if it has one, though not all do. If it does have a serial number, the manufacturer can be contacted for information such as drawings, etc. on the motor. Motor frame sizes are an important piece of the puzzle for proper installation. These give us the dimensions such as shaft diameter, shaft height, foot dimensions, etc. There are tables available online and in pocketbooks that exist will give you these dimensions. So, for example, if you go to manufacturer ABC and get a 256T and you need to replace that motor, and the only manufacturer that has one available is XYZ, as long as you get a 256T from them, it should fit exactly in the same place. One caveat to remember with this is that if it has a special letter designation on the end of the frame number, such as 256TZ, that means that it is a special build and will have either unique shaft size, unique shaft length, or something else that is unique to that particular motor, some sort of unique dimension. And so a 256T may not be a direct replacement. You have to pull up the drawings uh, and see what exactly the Z means. A lot of times it has to do with either shaft diameter or shaft length. A great resource to have in the field is called the Electrical Engineer's Pocket Handbook. It contains a table with most of the standard sizes for reference, along with some other valuable info. I will put a link in the description below the video. HP or horsepower is the rated output of the motor. In the US, NEMA uses horsepower for all ratings. However, if you have a European motor, it will be rated in kilowatts or kW. To convert kW to horsepower, kilowatts to horsepower, you need to divide the kilowatts by 746. This will give you the horsepower. The class box indicates the class of insulation for the motor. This will determine what temperature the motor can withstand internally during operation. The Hertz box indicates the design frequency of the motor. In the United States, and several countries, this will always be 60 Hertz. However, for many European and other countries as well, they are rated at 50 Hertz. DES or the design code. This is the design code of the motor and it determines the torque capabilities of the motor during start and under load. The insulation class of the motor is designated by a letter which indicates the temperature rating of the winding insulation in the motor. Here's a letter designation table from ANSI NEMA MG1, American National Standards Motors and Generators. Class A, maximum allowable temperature, 105 degrees C or 221 F, typically used for small low voltage motors. Class B, maximum allowed temperature 130 C or 266 F. This is commonly used for general purpose motors. Class F, maximum allowed temperature is 155 C or 311 F. Widely used for industrial motors as it provides a good balance between temperature rating and cost. Remember, as you increase the temperature rating, you increase the cost of the winding insulation. So you just don't want to always buy the highest rated you can find. Class H, maximum allowed temperature is 180 C or 356 F, used for high temperature application or motors designed for extreme environments. So it is important to look at the ambient conditions for which you're installing the motor. If it is a very warm location, you may want to make sure you get a insulation class motor that is appropriate for that location. Class F is a motor typically seen in industrial applications. It's the one I've seen most of. I have seen some Class H where we've had some peculiar circumstances that required a high temperature withstand. The design code of the motor designates the torque characteristics of the motor. This information is needed to ensure that the motor can start the load and maintain torque as needed throughout the startup. On the nameplate, in our example, the designated or the design code letter is A, which is a very high torque ability, peaking at about 75% of speed. When engineers are designing installations, they select a motor code based on a compromise of the required starting torque as well as the running torque. If the motor load exceeds the torque rating of the motor will come to a stop. It just cannot provide enough force to keep turning the motor. This is called breakdown torque. In the graph here, you can see that this particular motor, starts out with looks like to be about 150% uh, torque at the very initial start, and it peaks around 75% at what is that, about 260 foot-pounds of torque. A class D has a very high starting torque, but you can see it drops off rapidly, and class B and C fall in between those somewhere. Um, Next, we have RPM. RPM is the rated RPM of the motor at full load after slip is factored in. Remember that on an induction motor, it cannot turn at its synchronous speed, and there will be some slip involved, and this is what is indicated on the nameplate. The synchronous speed of this motor is 1200 RPM, but because of slip, its output is 1159 RPM. This is a 6-pole motor with 3.4% slip. Max RPM. Now, this particular motor is an inverter duty rated motor. In other words, it can be put on like with a variable frequency drive. As can be seen in the lower right hand corner of the nameplate, and we'll discuss that here in a bit, this is the maximum RPM that the motor can be ran at based on variable frequency drive inverter providing an increased frequency. In this case, it can be turned at 1500 RPM maximum. So we can increase that RPM by increasing the frequency. Code. This is the locked rotor code designation of the motor. This is used to determine the current being drawn at full voltage when the motor has a locked rotor. In other words, it's not turning. So let's talk here about synchronous speed. Let's discuss synchronous speed, number of poles, and slip in an induction motor. The synchronous speed of a motor is calculated by the following formula. Ns is equal to 120F over P, where Ns is the synchronous speed in revolutions per minute, F is the frequency of the AC supply in hertz, and P is the number of poles in the motor. As 120 times 60 is equal to 7,200, we can simply divide 7,200 by the number of poles to give a synchronous speed. This, of course, is in a 60 hertz system. In a 50 hertz system, you would divide 6,000 by the number of poles to get synchronous speed. Since the number of poles is not given on the nameplate, but we do have the RPM, we can use that to determine the number of poles. First, we will round up the RPM to the nearest even number in hundreds. In the case of this nameplate, instead of 1159, we'll round it up to 1200. We can then simply divide 7200 by 1200, giving us 6 poles. Let's go back. I missed something there. Slip can be calculated by subtracting the nameplate from the synchronous RPM. If you then divide that value by the synchronous RPM, it will give you the slip percentage. So in this case, slip is equal to 1200, the synchronous RPM, divided by 1159, the rated RPM, which gives us a slip of 41 RPM. We take 41 and divide it by 1200, we can see that we have 3.4% slip. Code. This is the lock rotor code letter, sometimes indicated by the letters LRC, so sometimes it may actually say LRC on the nameplate. This is a very important value to understand as it indicates the inrush of the motor when it's at a dead stop and energized. This is a value of current that the motor will draw with the rotor not turning at all. This value indicates the kVA per horsepower that the motor will draw with a locked rotor. We will get into this in a future video when we discuss overcurrent protection for motor circuits. Here's a snippet of table 430.7 in the NEC. So you can see here that if we have a class H motor or code H motor, that it will provide anywhere from 6.3 to 7.09 kilovolt amps or kVA per horsepower. Now this is at locked rotor, so this also means at a dead start, the second you close that contactor, that very first inrush, that is what it's going to see. So in our example nameplate here, the LRC code is H. This means that the motor will draw between 6.3 and 7.09 kVA per horsepower in a locked rotor situation. We take the worst case scenario of 7.09 and multiply it by the 20 horsepower, we get 141.8 starting kVA. This motor is a dual voltage rated motor. There will be a separate plate on the motor indicating the connections required for each voltage. So there'll be another little plate on the motor that'll show you um, how to wire up the motor if it's a 9-lead motor, etc. You will note that this motor is rated 230/460, which is a standard rating from NEMA MG1. The 230 volt configuration can be connected to a voltage supply of 208 to 240 volts. The 460 volt range is from 440 volts to 480 volts. Motor weight is just simply the weight of the motor. This information is useful in determining what kind of hoist will be needed to set it in place. So you make sure you have something rated for that weight. Amps. The amps listed in the motor has two values. These correlate to the two voltages listed above. So in this example, if the motor is wired for 230 volts, it will draw 54 amps. And when connected to a 230 volt supply, it will draw 27 amps when it's connected to a 460 volt supply. Service factor. This is the service factor of the motor. This rating indicates the motor's ability to handle temporary overloads beyond its rated horsepower, ensuring reliable operation under normal conditions. This value is required to determine the overload setting for the motor. Now, just so we understand here, a motor will try to draw as much horsepower as it needs. You can take this 20 horsepower motor, you can attach it to a pump or other piece of equipment that is requiring 30 horsepower, and that motor will output 30 horsepower. It will do so up until it exceeds its torque requirements. Once it reaches that breakdown torque, of course, it will come to a stop. But by doing that, you are seriously overheating the motor and you're going to shorten the lifespan of that motor. Power factor, this is rated power factor at full load. So continuous duty motors, separate overload device. This is from the NEC 430.32, section A1. A separate overload device that is responsive to motor current. This device shall be selected to trip or shall be rated at no more than the following percent of the motor nameplate full load current rating. Motors marked with a service factor. 1.15 or greater is 125%. With a temperature rise of 40 degrees C or less, 125%. All other motors is 115%. So if it's a surface factor 1.0, it would be 1.15%. Modification of this value shall be permitted as provided in 430.32c for a multi-speed motor. Each winding connection shall be considered separately. So if we look at 432C, 430.32c, selection of overload device, where the sensing element or setting sizing of the overload device is selected in accordance with 430.32A1 and 430.32B1 is not sufficient to start the motor or to carry the load, higher sensing elements or an incremental setting or sizing shall be permitted to be used provided the trip current of the overload current device does not exceed the following percentage of motor nameplate full load current rating. So motors marked with surge factor 1.15 or greater, you can go up to 140%. If it's 40C or less, you can go up to 140%. All other motors are 130%. If not shunted during the starting period of the motor, as if not shunting during the starting period of the motor as provided in 430.35, the overload device shall have sufficient time delay to permit the motor to start and accelerate. A thorough discussion of overload selection and settings shall be presented in a future presentation. So yes, you can increase the overload size up to 140% for a service 1.15. But just remember, doing so, you're going to increase the heat of that motor. You're going to shorten its lifespan. And last location I worked, our electrical engineer would permit uh, the motor overload to be increased to 140% for a short-term period. Typically, this happened because of either increased flow rates or a process fluid change on a pump. And so he would allow this in in order to give us time to get a larger replacement motor of the same size of the proper size to replace it. It's not something you want to do just indefinitely long term. Next, we have rating. In this particular case, this motor is continuous duty rated and a 40% or 40 degrees C temperature rise. On some motor nameplates, these two values will have their own box for indication. Uh, Continuous, of course, continuous duty in the code, anything running 3 hours or more within a 24-hour period. And it's rated for 40-degree temperature rise uh, over ambient. The NEMA nominal efficiency, this is simply the rated efficiency of the motor at full load. This is basically our input power divided, or our output, let's rephrase that. This is our output power divided by our input power. This motor is rated for Class 1 Div 2 locations, Group A, B, C, and D, as well as Class 1 Zone 2, Groups 2A, 2B, and 2C. The groups are basically the type of process that we have. For Class 1 Div 2, the temp code is T3C. For Class 1 Zone 2, the temp is given as a 160C. Both of these values indicate the maximum surface temperature of the motor under normal operating conditions. This is used to determine the acceptability of the motor based on the auto ignition temperature of the process where it is installed. So you may have a process with some sort of gas that has an auto ignition temperature of 180C. Well, in this particular case, this motor will suffice. If you look at the table from the NEC, table 500.8C, if we go down and we look at the T3C code, we can see that the maximum is 160C, which for the zone classification that was just given outright. In this section, if the motor has space heaters, some motors will have space heaters. If so, this section includes all the relevant information of the space heater. So it includes the volts, the amps, the watts, the temperature, uh, lead connection, etc. Not all motors have them. It, space heaters are used when the motor is de-energized to keep the windings above ambient temperature so they do not absorb moisture. This is typically interlocked with the motor starter so that when the motor is off, the heater is energized. And when the motor kicks on, it turns the heater off. In this section, it contains all relevant info to maintenance the motor bearings. This includes the recommended grease type, as well as the drive-in and opposite drive-in bearing numbers, which can be referenced for replacement. So if you got a bad bearing, you can look on the nameplate and say, oh, I got a drive-in bad bearing. That's a 6311. That's a standard SKF bearing number. You can go order a bearing and replace it. In this section, you see that this motor is inverter duty rated, and this section contains relative ratings for use with an inverter. CHP, this is the continuous horsepower frequency range of the motor, in this case, 60 to 90 hertz. CT, this is the constant torque frequency range of the motor, in this case, 1 hertz to 60 hertz. And VT, the variable torque frequency range of the motor, in this case, it is 0 hertz to 60 hertz. Now that we've gone through the nameplate and we understand how to read it, let's look at an application very typical in an industrial installation. In this case, we'll look at a pump. Our rotating equipment or mechanical engineer will provide us with the motor specs. This is based on the curve for the pump from which they will determine the required RPM and horsepower. From there, based upon the electrical supply, we can determine an appropriate motor for the application. So let's look at the basic work formula for a centrifugal pump, just so that we kind of have an understanding of how this works. Here's the formula, which is work is equal to density times flow rate times velocity of whirl at output times tangential impeller velocity at outlet. So the variables in the parentheses are inherent to the pump design. When he specs out the pump, it's going to give you these values. These two items are of interest. The two items that are of interest to us are the fluid density and the flow rate. The fluid density is determined by the process, example given, the type of fluid being pumped. A change in the process will result in a change of the work of the pump, which in turn will affect how many horsepower the motor is drawing. The flow rate is typically controlled by a flow valve that regulates how much flow the pump is putting out. As the valve opens, flow increases, thus work and horsepower increase. As the valve closes, less work and less horsepower is required. Now, typically, when you have an existing pump, let's say, and you got an existing motor, and the motor's been running fine for a year, and then all of a sudden it starts tripping out on overload. Well, the very first thing we want to look at, has there been a process change? Have they changed the fluid viscosity or density that pump is handling? If so, that can increase the workload. The other thing is, have they increased the flow rate? Either of those two will increase the horsepower required, which will cause a motor to draw more current, and well, it can cause a motor overload to trip. In the instances, as previously mentioned, where I've seen us go to 140% for the motor overload on a temporary basis, it was because of one of these two factors. And again, we did that temporarily until we could get a new motor spec'd out, designed and bought and installed to handle that change. So let's assume that the engineer has informed us that we need a motor rated for 20 horsepower and 1200 RPM. We also know that the supply for this motor will be from an MCC motor control center that is rated 480 volts AC. The motor used in our nameplate example will work for this application. Thank you for viewing this presentation. In our next session, Low Voltage Induction Motors Part 2, we will discuss the feeder conductor installation along with the requirements of the NEC. This presentation has been a production of Industrial Master Electrician channel. If you have any comments or questions, please post them in the comment section of the video. Thank you. All feedback is greatly appreciated. And see you in the next video.